Welcome back, everyone, to another episode of Learning as a Hobby, where I'm continuing with my series of teaching myself physics. And if you watched the last video, I'm starting out by going through Michael Spivak's fourth edition book entitled Calculus. In the last video, I went through my lecture notes for the book for chapter 1. And now I'm going to do the recommended exercises that he recommends in chapter 1 that you do, in the exercise set at the end of chapter 1. He recommends that you do question number 5, question number 24, and question number 25. There are a full 25 questions to the exercise set. There are other interesting problems in that set that I recommend that you take a look at. However, because the three recommended problems, 5, 24, and 25, are so long because they have several parts, I'm going, just to keep the video length here reasonable, I'm just going to go through those three exercises. But you should take a look at the other ones because there are some other interesting problems. I just don't want this video to be like 5 hours long. So it should take me about 45 minutes to an hour to get through these three problems just because they have so many pieces to them. So we'll start with question number 5. Before I jump into that, I do want to say one more thing. The next video, I'll be going through chapter 2 in part 1 of Spivak's book, because he talks a little bit about proof techniques there and some other definitions of number sets that we need for further chapters. So I'll start with my lecture notes for that in the next video, and then from after that, and I do the exercises for that chapter, I'll move on to this book here, chapter 1. I'll do in Theodore Schifrin's multivariable mathematics textbook. We'll start in chapter 1 on that one, and I'll alternate between the two books there. So I'll do one chapter in one book and another chapter in another one, and so on until we get through both of those books. So let's jump into question number 5 in Spivak's book. These questions do require that you know some proof techniques. So chapter 2, he does talk about a little bit of proof techniques, but I might actually make an entire video just on like sort of a basic introduction to proof techniques that you need in to be a math major, I guess. So let me share my whiteboard and we'll just go through the problems here. So I won't talk about how you do these proof techniques. I'll just do them here, and then I'll make another video maybe on how to actually do proofs in general. All right, so starting with question number 5, there are 10 parts to this problem. We'll go through them one at a time. All of these parts to question number 5 deal with the order relation defined on an ordered field, which we talked about in the last video. I'll write the actual questions down so you can, in case you don't have the book, so that you can see them. I do recommend that you try them. So once I write down the problem, pause the video and try to do them yourself before looking at my solution. This way you get more out of the exercises than just, passively looking at me solve the problem. So part 1 says this: if A is less than B and C is less than D, then A plus C is less than B plus D. So here's the proof. I'll do most of these with a direct proof. This one's going to be direct proof. So for a direct proof, you assume the hypotheses: let A less than B and C less than D. Then B minus A is in the set of positive numbers. D minus C is in the set of positive numbers, just by the definition of the order relation. And by closure, of the positive numbers under addition, that means that B minus A plus D minus C is in the set of positive numbers, and by the field axioms that we looked at in the last video, B minus A plus D minus C is the same thing as B plus D minus A plus C in the set of positive numbers. Therefore, B plus D is greater than A plus C. And that verifies part one. Part two says if A is less than B, then minus B less than minus A. Okay, proof. This one will also be a direct proof. Let A less than B. Okay, then B minus A is positive. Also, B is minus B, which I believe we proved in the last video. In other words, what this says is that B is the additive inverse of minus B. So B minus A is minus A plus B by commutativity, which is the same thing as minus A minus B is positive, which implies that minus B is less than minus A. Right, on to part three. Part three says if A is less than B, and C is greater than D, then A minus C is less than B minus D. Right, proof. So again, this will be direct proof. Let A less than B. And D less than C. Then minus C less than minus D by part two. And A minus C less than B minus D by part one. Right, that just follows from part one and part two. Right, part four says if A is less than B and C is greater than 0, then AC is less than BC. Right, so let A less than B and C greater than 0. Then B minus A and C are all positive. So C times B minus A is positive by closure of the positive numbers. And C times B minus A is the same thing as BC minus AC by distributive law. So by this equality here is by distributive law. All right, which means that AC is less than BC by definition of the order relation. Okay, so that proves number 4. Number 5 says if A is less than B, and C is less than 0, then AC is greater than BC. Right, proof. Let A less than B, C greater than 0, then B minus A and minus C. Oh, sorry, this should be, oops, C less than 0. And minus C is in the set of positive numbers by trichotomy. Okay, so sorry, this XP pen made my fingers fall asleep. So minus C times B minus A, which is the same thing as minus BC plus AC, is positive, which means AC is greater than BC. Right, next, VI. If A is greater than 1, what was this, VI? If A is greater than 1, then A squared is greater than A. Proof. Right, let A greater than 1. And that means that A is greater than 0 since 1 is greater than 0. So 1 minus A, sorry, A minus 1 rather, is positive, and A is positive. So A times A minus 1, which is A squared minus A, is positive, which implies A squared greater than A. Right, next one, VII. Which says if 0 is less than A less than 1, then A squared is less than A. Okay, so let A 0 less than A less than 1. Then again, A is positive. 1 minus A is positive. And that means that A times 1 minus A is positive by closure of the set of positive numbers, which implies A times A minus A squared is positive, which means that A is greater than A squared, right? Part 8. Which says if A is less than or if 0 less than or equal to A less than B and 0 less than equal C less than D, then AC is less than BD. Right, proof. All right, this one I'm gonna do by cases. Still gonna be a direct proof. So by cases, case 1. Without loss of generality, assume actually, I should probably say what the case is here first. The first case is A is 0 or C is 0. And I can say without loss of generality, assume A is the one that's 0. Okay, then AC is 0. And B greater than 0, D greater than 0 implies BD, B positive and D positive, which implies BD is positive, which means BD greater than 0 greater than equals AC. That shows that case 1 holds. All right, case 2 will be that both A and C are positive. Sorry, my finger's still falling asleep. I don't know if it's the position I'm sitting in or just this squeezing the pen too hard or something. I don't know. Case 2. Case 2 is A, C, both greater than 0. Okay, then B minus A is greater than 0. D minus C, same thing. By the hypothesis, right? So also B positive, and what else do I need? I want to show that AC is less than BD, so I think I need C, D. I think I need also, yeah, C is also positive by the hypothesis, then C times B minus A is positive by closure, which means that BC minus AC is positive, or in other words, BC is greater than AC. And see if I can fit this in here. B times D minus C is positive, which implies BD minus BC positive, which implies that BD is greater than BC. So by transitivity, that means that AC less than BD by transitivity, which is something that we proved in the last video. All right, what was that, number 8? Okay, next is number 9. Number 9 says if if 0 less than equal A less than B, then A squared is less than B squared. Okay. Proof. This one actually follows directly from the one that we just did. From VII, where A equals C and B equals D. All right, and lastly, part 10. Says if A, B are positive or greater than 0, and A squared less than B squared, then A is less than B. Okay. We'll do this one using something called a proof by contradiction. So for the sake of contradiction, assume that A be positive, A squared less than B squared, and A greater than equal to B. Right, so we'll have to do this in cases as well. So the first case will be A equals B. Assume A equals B. that implies a squared equals b squared, which contradicts the fact that a squared is less than b squared. All right, case 2. Assume a is greater than b, then a squared greater than b squared by part 9. Oops, part 9. And that also contradicts that a squared is less than b squared. And that exhausts all the possible cases. So that shows that the original statement is true. That's called a proof by contradiction. Right, and that's basically the end of question number 5. So we'll move on to question number 24, which involves another proof technique called a proof by mathematical induction. If you're not familiar with proofs by mathematical induction, like I said, in the next chapter, he does talk a little bit about that. So we'll go over that when I look at my lecture notes with you guys for chapter 2. And like I said, at some point in the future, soon, maybe I'll make a video about like basic proof techniques. Right, so this is question number 24. And there's 3 parts to question number 24. Before we get to the parts, he says, just for concreteness sake, we'll say that let A1, the sum A1 up to AN mean A1 plus A2 plus A3 All right, so just that's a note that he has in the question. So he says, let this denote that. Okay, part A, maybe I'll, should I fit it, see if I can fit it on this page? Let's see if we can. So part A says this, prove that prove that A1 plus AK is equal to, sorry, plus AK plus 1 is equal to A1 plus dot 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 up to AK plus 1. All right, so we'll prove that, like I said, using something called a proof by mathematical induction. So proof is by induction on K. There's 2 parts to a proof by mathematical induction. You have a base step. Oops, base step. Right, so the base step here will be K equals 1. So in this example, A1 plus A2 is the same thing as A1 plus A2. That's pretty much by just definition of a sum. So by definition of sum, right? Two, I just gotta relax my thumb for a second. All right, part two is called the inductive step. All right, so we'll say for the inductive step always starts with something called the inductive hypothesis. So the inductive hypothesis will be for any, for any, what's the word? For any k, I guess, k terms or k plus one terms. A1 plus dot 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 AK plus AK plus one is equal to A1 plus AK plus one. All right. So that's the inductive hypothesis. Consider then A1 plus dot 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 AK plus one plus AK plus two. All right. Then we can use the inductive hypothesis to write the sum that's in the parentheses as A1 plus A2 plus dot 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 AK plus one plus AK plus one. Oh, sorry, AK plus two. And then using the associative law, if you remember back to the field axioms, I think it was P1, property one, we can reassociate. Right, and the second thing that's in the brackets, that's a sum of K plus one terms. So that's the same thing as was it A2 plus dot 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 AK plus two. Okay, and that's the same thing. Yeah, so actually, I just want to make it clear that this is the case using this fact here, but I don't have space to write it. Let me, I guess I should write this on the next page. Let me just do it just to make it clear. Uh, I'll just recopy the last line here. So that, what did I have? One. Oops, two. This is the same thing as A1 plus A2 plus A3 plus dot 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 plus a and oh, wait, K, I have the last one is K plus 2, so this should be K. Oops, K plus a K plus 1. Plus 2. All right, and this is the same thing as, oops, A1 plus AK plus 2. And that is the proof by induction. So here in that this last bunch of equalities here, I'm using the fact that he gave us up here. Oops, where is it? This thing that I starred up here. Okay. All right, so that proves part A. Let me show you what part B asks us to prove. So 24 part B says prove that if n is greater than or equal to k, then A1 plus AK plus AK plus 1 plus dot 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 plus AN equals A1 plus AN. Okay, and again, we're going to use induction for this, so proof by induction on K. Right, so our base step, again, we start with K equals 1. All right, so for K equals 1, again, we just get the usual definition. So A1 plus A2 is A1 plus A2. Just by the definition of a sum. Okay, inductive step. Actually, hang on one second. Can I? Actually, I gotta redo the basis step. Hang on one second. Because this doesn't necessarily have to stop at 2. Let me redo this. Hang on. Because they're saying here that n can be any number greater than or equal to k. So let's do a1 plus and then in parentheses a2 plus dot 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 up to an. Right. This actually follows. This is a. Actually, this follows just from this part here. Not that I'm thinking about it. It follows right from this. So actually the base step here, this is a1 plus, and then here this thing here is this, again using the concreteness thing that he said, a2 plus a3 plus, dot dot dot, right? So this is actually a1 plus an by the star thing. Okay, so that shows that the base step is satisfied. All right, inductive step, assume that the property holds for some k. So for some natural number k, oops. I'm sorry, some k in a set of natural numbers. Right, and then consider, sorry, just gotta, my thumb is falling asleep again, sorry. Okay, so consider right, consider this sum here. The first sum we can rewrite like this by the question that we did a second ago, by part A. All right, and let me actually continue this on the next page so we have more room. I'll just recopy what I had here for a second. All right, here I can reassociate, so you're just using the associative law. So this is A1 plus dot 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 AK. All right, and this part here, what this equals, this is A1 plus AK. Right, and then the second part is AK plus 1 up to AN. And again, that's by star, right? That's that by that property, that by that so this is by star. By star, again, I'm referring to this thing that he told us to assume. All right, and this is actually equal to A1 plus AN by inductive hypothesis. All right, and that shows the inductive step holds. So the statement holds by the principle of mathematical induction. All right, that's part B. Let's go on to part C. All right, so here again, he gives us a definition. So let this be some sum formed from A1 through AK. And they want us to show that the sum A1 through AK is equal to A1 plus dot 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 AK. And he does give a hint here, so I'll write the hint just so you have it as well. The hint he gives is there must be two sums S prime A1 AL and S double prime AL plus 1 up to AK, such that the sum of the A1 through AK is equal to S prime A1 up to AL plus S double prime AL plus 1 up to AK. Okay, so that's the hint that he gives us. Let's prove this statement. Again, we're going to use induction. Actually, we're going to use a stronger form of induction here. In the book, he calls it complete induction, but I haven't heard that term before. I know it as strong induction. So, but either way, it's either complete induction or strong induction. It means the same thing. So we'll do this proof. By strong induction on K. Right, here's our base step. So here the base step will be for K equals 1. So in other words, we're showing that this is equal to this, which is obviously true. The sum of a single term is just whatever the term is, right? So that's okay. And then the inductive step. So here's where the strong induction comes in. Assume for all L less than or equal to K, that I'm sorry, for all K, sorry, this is induction on K. For all what do I say? It has to be strong induction. So all K, let's say K minus 1, all the way down to, I don't know, 2, 1, right? For some K in N. That SA1 A sub K is equal to A1 plus dot 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 AK. All right, so that's the inductive hypothesis. Now we'll consider SA1 through AK plus 1, right? By the hint that he gave us, actually, let me just write it here. So then for some positive indices L, there exists two sums such that SA1 AK plus 1 is equal to S prime A1, A1 up to AL plus S double prime AL plus 1 dot 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 AK plus 1. And I'll have to continue this on the next page, so let's do that. Let me just rewrite what I have here. So S1 dot 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 AK plus 1 equals okay. Now each of these sums, the S prime and the S double prime, are sums of terms that sums of less than K terms, right? So this is equal to A1 plus AL plus AL plus 1 plus dot 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 plus AK plus 1 by inductive hypothesis. All right. And each of these is, these two sums here, A1 is equal to A1 plus dot 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 AK plus 1 by part B. And that proves the third part. Okay, so all three of those parts are proved now. And what 24 says is that the associative law applies to a sum of any length. So that's what 24 is getting at. All right, so that's the proof for number 24. That was quite an involved proof, actually. Let's move on to question number 25. Right, and did I not write down the problem here? I have to get the problem from the book. It looks like I didn't actually write the problem on that page. Just bear with me for a minute. Oops, I'm looking at the wrong part. Here it is. Okay, so here's the problem. Suppose that we interpret number to mean either 0 or 1. And plus and addition and multiplication to be the operations defined by the following two tables. Right, so he gives us two tables. So for addition, oops. So the addition table looks like this, and the multiplication table looks like this. And he wants us to check that the properties P1 through P1 through P9 all hold. Even though 1 plus 1 is 0. Okay, so he wants us to show that this verifies the field axioms, in other words. This is actually an example of a finite field, which is sometimes denoted by the symbol for the integers with a subscript of 2. This is addition. This is the integers modulo 2. Let me go back so I can see what the list of the field axioms are, so I can do them one at a time. All right. So let's go to the next page. So P1 is the associative law. For addition. In other words, A plus B plus C is equal to A plus B plus C for all A, B, C in the set. Right, so they want us to show for P1 that that Z2 basically satisfies the associative axiom. I can skip the ones when A, B, and C are all identical. So in other words, if A equals B equals C, then it's trivial. So let's deal with the cases where they're not equal. So consider I guess we could do 1 plus 1 plus 0, which actually, if you notice, is the same thing as 1 plus 0 plus 1 by, the commutative. Oh, no, we haven't shown that yet. Sorry. Hang on. We do have to show this. Sorry. 1 plus 0 is 1 plus 1, which is 0. And if I do 1 plus 1 plus 0, we get 0 plus 0, which is 0. And so these are equal. Then we could do, say, 0 plus 1 plus 0. And that would be 0 plus 1, which is 1. And if we do it the other way, 0 plus 1 plus 0, that gives us 1 plus 0, which is 1. So these are equal. Then we could do 1 plus 0 plus 0, I guess. Oops, let's check the other way. All right, that checks out. Then what's next? 1 plus 0 plus 1, I think we have to do. That checks out. We need to do what else? We did 0 plus 0. We need 0 plus, we did 1 plus 0, so we could do 1 plus 1. All right, that checks out. Okay, and let's see, what else am I missing? We have 1, 2, 3, 4, 5, 6, 7. I need one more. Need another one with a 0 in front. What didn't I do? 1 plus 0, 0 plus 1. Oh, sorry, 1 plus 0, and I did 1 plus 1. So 0 plus 1 I have to do. So here I have, what is it? 0 plus 0. Right, these are equal, and that exhausts all the possibilities. There's only 8 combinations you can have, right? 2 for the first, 2 for the second, 2 for the third. So 2 times 2 times 2 is 8. So that exhausts all the possibilities. So that shows that P1 is satisfied. Then we can go on. Oh, does Zoom not let you do more than 20 pages? I may have to erase something then. I'll erase this page. Or maybe I should go back to the beginning. What should I do? Let's go back to the beginning, and I'll just erase it this way. I can just keep going to the next page. Clear all drawings. Right, P2 is, I think that's the commutative law. No, existence of additive identity. Which, if you look at the table, it should be clear. Oops, keep doing that. So clearly 0 acts as the additive identity because 0 plus 0 is 0. And 0 plus 1 is 1, which is the same thing as 1 plus 0. Okay, and actually same thing, you can tell right from the table that there's additive inverses as well, which is what number is that? P3 is additive inverses, so I'll just do that right now. So P3, existence. So here you can see the additive inverse of 0 is 0, and the additive inverse of 1 is itself. So the elements are their own inverses, right? P4 is next, which probably is commutativity. Yes, for addition, P4. Addition is commutative. And again, if you look at the table, it's clearly commutative. One way you can see it is just that the table is symmetric through the diagonal. But if you look at 1 plus 1, that's obvious. The ones that where the elements are the same, it doesn't make a difference, right? This is the same thing as 1 plus 1. Same thing with 0 plus 0. Uh, 1 plus 0 is 1, which is the same thing as 0 plus 1. So commutativity checks out. Next is P5. What's P5? Associative law for multiplication. Again, there's 8 things that you'd have to check. So if you check all these, you'll see that they work out. So what else? 0 times 1 times 1. Okay, well, what else do I need? 0 times, I did 1 times 0, so 0 times 1. And then you do all the ones where the first entry is 1. And 2 more, 1 times 0 times 1. All right, and that verifies P5, so onto P6. And those associativity is probably the most annoying ones, but so sorry, that was P5, I think. So P6 is next. P6 says existence of a multiplicative identity. Right. So again, if you look at the table for multiplication, clearly there's a multiplicative identity. 1 times the multiplicative identity is 1, right? So 1 times 0 is 0, 1 times 1 is 0, and so on. So 1 times 0 is 0, 1 times 1 is 1. So 1 is the multiplicative identity. And the next one is probably existence of inverses, so I'll just do that. Okay, existence of multiplicative inverses. Right, so the multiplicative inverse means that for any non-zero entry, for any non-zero element, there's a number that gives you, when you multiply by it, gives you the multiplicative identity. So the only non-zero entry here is 1, and 1 times 1 is 1. Okay, so there are multiplicative inverses. P8 is about the fact that multiplication is commutative. And again, if you look at the table, you'll see that it is, because the table is symmetric through the diagonal. All right, but you could check, you could check 1 times 0 is 0, which is the same thing as 0 times 1. 0 times 0, it's the same thing as 0 times 0, obviously. They're the same element. Same thing with 1 times 1. You don't really even have to check because they're the same element, but right, so that works. P9, I think, is the distributive law. So multiplication distributes over addition. And again, there's just a bunch of cases that you'd have to try. So for example, 0 times 0 plus 0. Right, then 0 times 1 plus 0. So you just go through all the, all the options. And here, since we already proved addition is associative, actually, we can save ourselves a little bit of work. 0 times 1 plus 0 is the same thing as 0 times 0 plus 1 by commutativity. So we could do next, let's see, 1 plus 1. Oh, I just realized there should be a 0 here. 0 times 1 times 0 times 1. That checks out. What else? We need 1 times 1 plus 0. Right, and again, by commutativity of addition, that's the same thing as 1 times 0 plus 1. We can just skip that example. We don't have to show that. What am I missing? 1 times 1 plus 1. Let's not plus 1 times 0. All right, that checks out. What else? I have 1, 2, 3, 4, 5, 6, 7. Did I do 0 plus 0? No, I think that's the last one I need to show. All right, and that verifies P9. Okay, guys, that was a long video. So let me just stop the share here for a second. Okay, so that's the end of I proved all the questions that he asked us to do in the chapter chapter one. Like I said, you should look through the other problems in the chapter exercises for chapter one, because there are some other interesting problems in there. But like I said, just for the sake of the length of this video, I'm just going to stick to the ones, at least right now, that he told us to do. So that's P5, that's 5, 24, 25. The next video is going to be on part one, chapter 2 in this book, my lecture notes, and then we'll do some of the exercises for that chapter as well. And then we'll move on to Theodore Schifrin's book, which you can see right here. All right, guys. So I hope you enjoyed this video. Leave a like and subscribe if you want to see more of this type of stuff. And I'll see you in the next one.